Yeah, I want to talk a little bit about some of the work that we did at Bot and Dolly post-Gravity. I joined the company shortly after Gravity was finished and came in at a really interesting point where we had kind of the technical success that came from Gravity and Asa and team's work there and the foundations of a motion control system and really sort of a general cinematic automation tool. And we also had inbound interest based on the work we did on Gravity for work in the visual effects world, but also for sort of broader sets of applications in creative applications of robotics. So I'm gonna pull back a little bit from the VFX world in my short presentation and talk about some of the other work that we did at Bot and Dolly. So I thought rather than doing that chronologically, it might be refreshing to talk about it in terms of kind of the design space we're exploring. This is the first time I've tried to articulate this stuff, so it might be a bit half-baked, but I think there's some interesting overlaps with computer graphics, and that's going to be the kind of the lens I try to use to look at some of the Bot and Dolly work. So, I think the design space that both robotics and computer graphics share includes actuation. In robotics, this means moving motors and lots of other things. In graphics, it usually means control of pixels. So, I think of applications in computer graphics actuating pixels in many cases. We also have sort of a dimension of sensing. So this is an example of photogrammetry and what computer graphics can achieve when it combines sensing and algorithms and control of pixels. And then there's another dimension that we think about, which is time. So here we have control.
Ian, we're not seeing your screen.
Oh, no. Is this visible?
Yep, got it.
Okay, apologies for that. I'm going to step back just a second. So thinking about actuation, control of screens, sensing, and combining that with control of screens here for photogrammetry. And now this dimension of time, which lets us do animation. And then when we combine all these things, now we have human input devices. So this is the original mouse from Bell Labs. We've got a cave 3D visualization environment. And here we are, sensing the pose of a human's head. We're actuating pixels being displayed by projectors and potentially also the lenses of the goggles that these folks are wearing in the cave. And we're doing that all over time. And then there's another dimension, which is about how we kind of evolve our sensing and actuation over time. What this means now is that we get to build logic. Here might be game logic, it might be autonomous control of virtual agents that let us, fly a TIE fighter in a virtual reality environment. It might be about doing physical simulation. So here we're not doing any sensing in the external world, but we are, focused on how we're evolving our pixels over time. So in robotics, I think we actually inhabit a very similar design space. Some important differences are that when we talk about actuation, there's mass and inertia involved. There's physical tolerances involved. So, this is a pretty major shift in mindset and kind of where a lot of the dragons lie. It has implications for safety. It has implications for the sort of control paradigms that we need to use for the design tools we use. For everything that these domains share, I think mass and inertia kind of is what distinguishes it to a great degree. Got to think about power. Obviously, the sensor modalities we have access to are usually broader in the robotics domain. So We'll look at some examples of that. Time resolution in computer graphics is often limited to, say, 30, 60, 120 hertz of control. In robotics, we're more often working with a range of sort of time resolutions that may stretch to kind of the 5 kilohertz range of resolution for motor control. And then in the way that we sort of evolve these things over time, because we're dealing with massive inertia, we're doing different kinds of planning. And because we're dealing with physical tolerances and sort of the uncertainty of the physical world and noisy sensor measurements and physics, we often have to do estimation of noisy signals. So, at Bot and Dolly, we thought about how to do animation and sort of take what we knew from computer graphics animation and apply that to the robotics world. So here's an application doing some milling on a piece of acrylic. So the actuation here is a robot arm and an end mill, where this is a pre-baked animation at 24 frames per second. The animation was generated from data in the form of a vector graphics file. Here we did animation for the Blue Man Group in Las Vegas. Actuation again, robot arms and end of arm tooling. The sensing problems involved here had a lot to do with the safety hardware that allowed the Blue Man Group to operate in safe proximity to the robots. So basically different segments of animated motion could be triggered by the use of safety mats and laser fences and other forms of monitoring the workspace that they were operating in. And here we use the tools of character animation. So a lot of forward kinematics animation tools in Maya and the tool set that Asa was describing before. We did some work animating large props at Wynn Las Vegas. We did some work prototyping an amusement park ride. And here, the way that we were evolving state over time used physical simulation, and the sensing use involved offline calibration with an IMU to help us sort of measure predicted versus actual G-forces that we would be imparting in this amusement park ride. We looked at the world of parametric design, and I think this is an interesting example. Oh no, my video does not seem to be showing. Oh, there we go. This was an application in fabrication. So this was the work of my colleagues, largely Matthew Bitterman and Kendra Byrne, using the parametric CAD tools of Rhino and Grasshopper to build structures that can be described with a small number of parameters. Here, the programming was constraint-based. So we constrained the angle of these mirrors to sort of create this effect based on the position of moving head stage lights. So again, this is about kind of different paradigms of programming actuation over time. This is an application using motion capture that involved a lot of calibration to get a lot of the nodal point calibration correct, but the end result was repeatable handheld camera moves. And this is a project that got a lot of attention called Box that coordinated the actuation of robot arms, cameras, and projectors. But I think the idea that I want to close with is that I think what really actually put Box on the map for us at the time was that it wasn't just a technical demo, which it was, but it also incorporated storytelling and visual design and sort of that combination of factors that Asa was talking about on the gravity set. And so, in closing, these things can do everything I just talked about. The actuation problem is the simple one, the sensing problem. is hard, and the autonomy problem is hard. But what distinguishes it from kind of the rest of the design space is the human element of having a story to tell. And so I think, my hope is that we kind of continue to explore this design space as computer graphics practitioners and robotics practitioners. It's huge. There's so much to explore. I'd love to map it together. And to a point made earlier, what is a robot anyways? In my opinion, it's anything sort of operating in that design space, and that's a very inclusive category. So I hope we get to make awesome stuff together. And yeah, feel free to reach out if you want to chat. Thanks.